So let's get started. Hello, good morning, and good afternoon and good evening, everyone. Thank you all for joining this webinar. So I'm JC from Texas Instruments, Senior Expert PRU ICSS Industrial Ethernet segment. And I have Christof, my colleague alongside. Christof, could you please introduce yourself?
Yeah. Hello, everybody. My name is Christof Vogt. I'm senior expert in stack development at TI, and by this responsible for integration and development of our field bus stack products. Thank you.
Okay, thank you, Christoph. So, participants on the right side, you can find a comment window. So, please do post your questions. We will try to answer them at the end of the webinar. So then we can start. Okay, all right. So, as you all see in the banner here, so today we are going to look into the Gigabit protocol enablement on the production floor. And as we all know that the market is moving towards the gigabit standard and vendor neutral solutions for the next generation industrial automation. So here OPC UA FX is the one interoperability technology and the game changer which is going to be in this gigabit transition. Then, so before we close this webinar, you will get to know the challenges what we are facing in the legacy Ethernet protocols. Basically, what's happening in the brownfield and what are the real challenges when we have greenfield like OPCUAFX inside the brownfield automation as well, and more little deep dive in the OPCUAFX technology itself. We will get to know the controller to controller communication, and then we'll also get to know the controller to device communication use cases as well. And next, we will look into the TSN, that's time sensitive networking, and then the role of TSN on OPCUA FX. And finally, we would like to get you walk through on the TI's ICSSG, the Industrial Ethernet subsystem, and its reference software architectures and the abstractions which are going to accelerate the OPCUAFX product developments, and then so that the system integrators or the device manufacturers and the process automation solution providers will get to know, and also to learn the right hardware and the software piece to build the OPCUAFX products, and they can also understand how they can prototype quickly. So this is the a small list of agenda which we are going to look. And finally, I would also like to say that we are not going to look into the fundamentals of OPCUA protocol itself. Rather, we will focus more on the OPCUA FX and the need for TSN, and then also the right hardware and software piece to build the products around it and accelerate the OPCUA FX ecosystem itself using ICSSG. Right. So I'll move to the next slide. Right. So I'm pretty sure you could have come across this kind of architecture in several forums. So this is the industrial automation pyramid that's starting from the factory floor to the ERP system, where we have PLC and SCADA, and then the gateway layer, and there's a ERP on the top. So if you look into this architecture itself, on the right side, you can see that there are several industrial legacy Ethernet protocols are listed, and they have different in a different by different vendors. and which are installed in the machines which is in the market as of now. So the challenge which I would like to highlight here is that the protocols listed here are tied to the specific vendors. So this creates fragments in the entire industrial automation ecosystem itself. So the thing is like when it comes to the key challenge here, as I said well before, you would have known this architecture, but there are some key challenges which I would like to pick. So the one is the real challenge I see from our customers or in the real use case is the engineering tool. So if you get a PLC from a vendor A, let's say here I have put a machine A where you have an PLC vendor, and there is a machine B with a different PLC vendor. The thing is they come up with an engineering tool along with it. So these engineering tool will help to configure the controllers, that is the IO controllers and the IO devices in the network. So these engineering tools are not interoperable as of today. Basically, you cannot use a vendor A engineering tool to configure the machine B or the vendor B product. So it is more tied up with a specific implementation and a specific compatibility and a specific configuration as well. So that's the one major reason why an engineering tool is not compatible in the real world today in the legacy Ethernet. If you look into the other side of it, that is the data semantics. So these protocols have their own way of data semantics or the data representation, how it is uh, put or how it's supposed to be communicated between the controllers and devices. So there are also an specific program logics which are available in the vendor controllers. So you can write logics with whatever the language they have developed. And the thing is like mostly they need an separate network engineer or the operator to operate or handle such kind of data semantics. So the devices which you're seeing that is using a different protocols, if they wanted to converge, let's say if the machine A wants to talk to the machine B, typically there are gateways. Often they call a component called gateway that is available in the market, where they make the protocols to talk each other. So this means you have to buy a newer device and put in between the two controllers and make them talk each other. So then definitely it's going to be the higher in cost, and also the complexity is going to be high in this case. That's the one major problem. And the second is the CRA compliance. So the CRA means that it is an cyber resilience act, which is enforced in Europe region. So what it actually means is that the industrial Ethernet products or the digital products, they should have an cyber security inbuilt going forward. They cannot have an security without they cannot have a product without a security. So the adoption of an CRA in the existing legacy products is becoming slower because they have to completely redesign the existing product as of now. So these are some of the real challenges which we are seeing in the legacy Ethernet, that's the brownfield architecture. Then, okay, now with OPC UA FX, that's the OPC UA field exchange. It's a little bit extension on top of OPC UA. This is bringing an a standard and to make the devices and the controllers to work interoperable, and they have the security inbuilt, and there is an high-end data semantics and more data modeling to make the controllers and devices from different vendors to talk each other. So they are making the language more common so that they can talk each other. And then the OPCFX is also going to solve the security limitations which we were seeing in the previous slide, because the OPC itself has an security inbuilt there. For example, they have an handshake, security handshake, and then they enforce security algorithms to pack the OPC pops up data messages or whatever it is. And the main thing is like OPC is not an vendor lock-in. So say for example, you have a lot of open source tools today to configure an OPC client server or the OPC pops up, or you can also browse the information model of OPC UA using the open source tools. So it has nothing to do with the vendors. You can download the tool from online and you can use it in any machines or any vendor controllers. And finally, OPC FX is going to support the convergence of IT and OT networks. That is like you have an different uh, uh, messages or the packets on the wire. So OPC is along OPC FX or paired with TSN is going to shape the network in much more efficient way, which will make the communication deterministic. So field exchange is always like enhanced with along with the TSN technology, so that they guarantee the latency, and then they can guarantee the like determinism, like, and then the bounded latency, etc. So that's on the reason why TSN is paired with OPC FX to make it more deterministic. On the right side, there are like two blue color arrow marks which are going where we have marked that as C2D and C2C. So the one which is you are seeing on the horizontal, that is controller to controller. So there are like two parts OPC FX is coming up with, that is the controller to controller communication and then the controller to device. So when it comes to the key differences between the controller to controller and then the controller to device is that the first, the scope are well defined. So say for example, if you're taking a profile that is controller to controller, that's like you make different vendor controllers to talk each other. And when it comes to the controller to device, it goes down to the sensor. So in short, like if you want me to put the say for example the latency for controller to controller use cases pretty small, like we need like 1 millisecond minimum. And if you take the controller to device, it can go down to the microsecond range, like 100 microsecond, because as I said well before, controller to device is going down to the sensor. And yeah, there are like applications like motion control, like sensors and actuators, which tend to send the data to the controllers at lower cycle time. And the third is like the controller to controller will have an higher resource constraint, whereas the controller to device will have only the will require only the lower um, footprint devices, right? So these are like two profiles what OPC UA FX is, has uh, brought up to adopt it, uh, and to make use of it. So on the top, you can see one blue color box. Uh, that's the small example on how an OPC UA FX controller to controller stack looks like. So you can see like three components. One is the automation component. So think of a PLC, right? So the PLC is called as an automation component. And there is a functional entity, And for example, the functional entity is like the application which is running inside the controller. Let's say a temperature control application, right? It's a application or the task that is running inside the controller. And the third one is the asset. So let's say it can be a logical or the physical asset. When I say logical, let's say you have a firmware on the air update, right? So the firmware is one asset. And finally, when you wanted to make the controllers to communicate each other, they have a connection manager module which is running inside the automation component uh, that will make the functional entity between the two controllers to talk each other. So that's how the OPCUA FX, the software design itself looks like. And the thing which I would like to stress in this slide is like the OPCUA FX itself can coexist effectively with the legacy Ethernet on the same network by using that shared infrastructure that is going to be the TSN, that's time sensitive networking. So it's not like uh, the transition is going to be like replacing legacy. It's like making the existing legacy Ethernet to work along with the OPC FX, and then that's how the transition is going to happen gradually. And and today the uh, product developers can put the OPC FX in the field, and they can make sure that's working well with the existing infrastructure on the legacy domain itself. So the system integrators and device manufacturers and the process automation solution providers now they need a right TSN device and robust and performance microcontrollers which can go down to the C2D use case, and vendor neutral engineering tools, which OPC UA itself is addressing that. So we are going in the upcoming slides, we will see how the right TSN device is going to look like, and how and what type of MCUs that is going to help down to the going down to the sensor level, right? So okay, and this is one architecture which I would like to show to you. So you can see it's a layered architecture. You can see from the bottom it's network, and there is an L2 layer 2 that's completely the MAC, and L3 plus, and then the finally the PCA or host. So what we will try to get to know in this slide is you will have a complete understanding of a system architecture when an OPC FX sit on top of TSN, how it's going to look like. So that's the system view where you can see several components in this picture. In L2, you can see a lot of TSN protocols, and in L3, you can see uh, an network or IP stack, and on the above, you can see an OPC UA FX. So on the topmost, you can see a small keyword that's PCI or host. So let's say you have an OPC FX SDK, right? So today, for let's say if you take an IO controller, so the IO controller manages the entire device network. Like you can have huge number of devices, IO devices. But when it comes to the IO controller, uh, the challenge is like when you have an uh, like an host CPU, and if you have an option of PCI, which is going to open up running the FX SDK or the FX stack, either on the PCI root complex on the remote side, and it will make the IO data to transfer over the PCI, and on the endpoint side, you will have an uh, network stack, and you will have an Ethernet drivers and the low-level drivers to send the data over the MAC, and to make this OPCFX communication. So the reason for having a PCIe and a host processor in today's world is I see a greater advantage. One is like if you have an let's say an R5 system, which is like a 32-bit real-time processor, that's purely built for the real-time capability, right? So you can run the motion controller application in the R5, right? And to collect the application data unit. But if you want to run the a bulky stack or stack services, let's say OPCA methods or OPC services, you can simply run it on the PCI side, which is not time critical. Let's say if you take A53, you can run an ARM processor or the x86 PCI host, where you can run the complete OPC FX SDK, right? So this is like to make the tasks offload and make it much more deterministic when there are like multiple applications is planned to run on a controller. So controller is always will have multiple tasks as it's managing more number of devices. So you have, I mean, when you're building a OPCFX product, you need an you need an host and a PC kind of subsystem to offload some of them on the x86 if you really need it, or you can simply use multiple core MCUs like A53 plus Linux. You run the OPCFX SDK, and R5 you run the motion control tasks, and then you can run the low level drivers on the R5 to send the data to the below layers. So it's purely kind of how you want to have a product, but the thing is like you might also need an multi-core processor to make the OPCFX to be more deterministic in nature, right? So in L2 you can see a lot of TSN protocols. I believe you would have come across most of them. So quickly put it in one line. So first is the 802.1 AS. It's a time synchronizing protocol, which will help you to synchronize the nodes in the network. And there are like three small components which I've put it here. One is TTS, another one is hardware time stamping, and third one is PPS. So TTS is one module that's the time triggered send. So whenever you put a packet on the line with the timestamp, it goes on time. So you need a hardware with a reliable um, timers to send the real-time packets on the wire on time. And then the hardware timestamping, which is purely used for PTP event messages to generate a timestamp and capture it and put it in the packet and send over the network. And last is the PPS, like pulse per second. They are used to measure your jitter in an in an multiple nodes in a network where you don't have a software option. You can just tap it on the hardware and you can understand how well your TSN device is behaving. So QBV is one used for scheduling the traffic. So you have multiple traffic class, then you can schedule it and you can send it across. And then QBU is purely for the preemption when there is a high priority packet on the port queue, and then there is a low priority packet which is already in the forward direction and it is started to forward. And if the TSN switch or the MAC layer finds an high priority packet, it preempts the low priority one and it sends the high priority traffic out. And there is an 802.1 CB, which I would say that's for completely for the redundancy. And OPC FX is looking for a redundancy protocols where FX can work together with CB to duplicate the frames in two different ports, and then they can eliminate one on the redundancy path. And then the QCC is like definitely a configuration protocol where it involves some amount of work from the YANG. That's the top layer where you can see the TSN SDK should have the YANG model, which works along with the netconf. And then you can see the 802.q VLAN. So there are like uh, the packet has its own quality of service. So you to identify the packets, you can use VLAN plus priorities to differentiate the packet and make the quality of service successful in the system, right? So you need an 802.1q as well, and 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 then if you look into the one more layer down, you can see two things. One is the store and forward and cut through, and the other thing is port queues. So store and forward is when there is a packet in the forwarding path, and if it's a non-critical or let's say an NRT packet, you can put it in the store and forward and it can go later. But whereas the real-time packets, definitely it's time bounded. So you should the TSN capable switch should have an cut through capability to send the packet uh, immediately once it receives the smaller chunk. And then the HSR and PRP, that's one technology you really need it. So let's say a smart grid substation, right? So today OPCUA is running in smart grid as well. So in the smart grid, if you want to duplicate the OPCUA packets, you need an HSR and PRP to duplicate the PubSub messages. We are sending it on the alternate paths, and the OPCUA FX controller itself will act as an DAN H. It's an HSR term where it will publish the DSMs, basically the dataset messages in the multiple directions. This will ensure the zero recovery time and reliability. So HSR PRP is really a practical consideration in OPCUA world, I would say. So these all the small components and pieces in terms of TSN, the hardware features, and on above the software pieces, which are really required to make the OPCUA FX to be product to be successful. And so now I believe you understood the complete um, uh, software and hardware requirements which is needed for the OPCUA FX uh, product, and how which will helpful to be accelerating it both the for building both the controllers and the IO devices. So next, and here comes this is the uh, most interesting part, that is ICSSG, the Industrial Communication Subsystem. So in this slide, what we are going to look into this is how the ICSG is going to enable our customers or the device manufacturers or the process automation vendors to quickly build the OPCUA FX product leveraging the ICSG. So if you look into this pyramid, right, in the bottom layer, you can see that ICSG subsystem is mentioned, but in the previous slides, there were like factory floor and PLC. So we believe ICSG is the future-proof solution, which can support developing and um, factory floor sensors or devices and controllers with TIMCUs along with ICSG, where you can have an OPCUA FX along with TSN to make the gigabit network to work seamless. So that's why we have put the ICSG replacing how it's going to help the controller and device development. On the right side, um, you can see there is a TSN switch, which is going to act as an uh, network infrastructure for enabling the legacy Ethernet and also the controller to controller communication on a same network infrastructure, right? So as you can see this entire architecture. So this is we see that ICSG is going to be a one fit for all, and when it comes to the TSN, there is a standard evolving that is called I IEC 60802, which is an industrial automation TSN profile. So in the TSN world itself, there is an automation profile which started to evolve. Um, these profiles has an stringent requirements as well. So let's say in a controller, you will have several tasks like background task, and there is a main task which is executing periodically or cyclically, and there is an process driven tasks like IO data, or which is like task that is triggered by an event when sensor threshold is reached. And there can also be an control loop task which is bounded to the working clock. Uh, Working clock is tied up more with the PTP time scale. And in these kind of industrial application, there are like several tasks like this, which will be running on an one controller or one device. So the TSN underneath is going to guarantee all these application traffic to schedule seamless. That's one. And second thing is the 60802 itself has a stringent requirement, as I said well before. That's uh, the transmission time at which when you put the packet in the port queues, and when it leaves on the wire, it should be like less than or equal to 10 nanosecond. So these are some stringent timing requirements which is really coming from 60802. So you need a product that can satisfy all these kind of stringent requirements uh, to meet, right? So there is an local clock in the TSN world that we call it as working clock, which we adjust based on the PTP time scale. So what it happens is we do have a nominal frequency requirement like 50 ppms and all those. So for this, we need a right TSN endpoint or the switch. And the next thing is like we need a support for TSN protocols. As I said well before in the previous slides, there are like several TSN protocol requirement for making the OPCUAFX product to be successful. And ICSSG has a provision for all these protocols which we have implemented it today. And third is obviously certification. How your product is getting certified is one hot topic when you build a product. So OPCA, I mean, uh, sorry, the TSN, once you have an software working, you need to certify it. And the TI SDK, TSN SDK is an Avenue certified. We run tests against the Avenue test suite. And we do also an interoperability test around it. So you need an certified stack also in your products. And the last is the industrial communication support. Like you need an support for legacy industrial Ethernet, like Ethernet IP or Profinet or EtherCAT, like many protocols, which is already part of the industrial communication SDK, where ICSG is already enabled to work with all these protocols, and OPCA is one such. And then the last is the init, like the Ethernet interface to have an direct access to the packet to the host directly. So say for example in Linux we call express data path. Once the packet is received, it's directly given to the host, so it doesn't goes through the IP stack. So uh, in OPCA we have such kind of requirements as well. Say for example in OPCA we have an layer to raw Ethernet transmission, uh, which ENET is going to provide you such kind of provisions to send and receive packets. So this is how the ICSG is enabled with TSN and OPCUAFX, and enable with the features to support integrating the OPCUAFX faster, and how the ICSG is ready to adopt the OPCUAFX technology itself, right? And next, here is the internal architecture of ICSG, and you can see that ICSG has two. Um, I mean, like there are like 6 cores, which are RISC CPU cores, and it's highly programmable. You can program the cores, and then we have a, a memory inside the per PRU core, and there is a broadside RAM as well. And the highlight here, which I would like to show, is that the data processing and the data movement accelerators, which you can see a lot here. So say, for example, the CRC16 and 32 hardware accelerators is for calculating the CRCs in much more faster way, where you can, let's say, if you have a pops up message and you wanted to like have a calculate and CRC, you can just simply offload it and it will give you the CRC. And then the task manager, which I will go through in the next slide. And third one is like we have an support for an several like let's say an MA support. That's the Ethernet, which we are going to talk about in next slides. And the fourth thing is like an spin lock, just to make sure that the tasks are like protected. And then there is widgets, high data movement accelerators, or widgets, what do we call. So you can see that X for VBus and X for DMA, the X for 2TR, those are the widgets which will help you to move the data faster. So it's not like a mem copy, it's rather it's a completely hardware offloaded. You can move the data in a few clock cycles. Like you can move using the X for VBus, you can move in 1 clock cycle, move the data in 1 clock cycle, right? So there are like several hardware features which are actively used in our TSN implementation to make the solution more deterministic and different from the other vendors. So this is these are like some of the highlights which are there for ICSG. And so one last point which I'd like to highlight is this is the complete ICSSG. It's a gigabit, and there is an cut down version that's called ICSM, where some of the accelerators are not available. That's purely for the device, IO device kind of use case, and where the controller can take the ICSSG, the higher end version, so that they can fully utilize the hardware resources. And let's come to the real implementation, or how we can make the OPCUAFX to leverage some of these components. So on the top, you can see that the OPCUAFX SDK. So we will have an vendor neutral SDKs from different third parties, or the vendors whom we are in working with. So we'll not have a vendor lock-in stack, rather we'll have a different vendor stacks on the top. And there is a TSN SDK which is already available in our SDKs, where you to work with this below TSN layers, right? And this in this slide, you can also see that there is an LLD, that's a eNet LLD, low-level driver for an faster data path. And then there is also an HAL, an abstraction layer, where if you have an your own host processor, you can just use a host processor along with ICSG, and use the HAL driver to communicate with. So I will go with some of these components which I have mentioned in L2, which is going to support the OPCUAFX in the next slide. But I will not go through the TSN protocols, but rather than I will go to the components that's which is highlighted. I would like to highlight to implement OPCUAFX in a more feasible manner. So the first thing you can see that I have highlighted an real-time and the non-real-time task. Uh, so there are like different traffic types, as I said well before. There are non-real-time traffic and there is a real-time traffic. So there is an hardware task manager in our ICSSG. It's completely an hardware-based context switching, and it's also priority based. So what it happens is, like, let's say there is a use case where you have a forwarding packet and there is a local injection, that is an ingress packet, and the forwarding packet is already on transmission, and then you have a local injected packet. When your Mac sees it, the 802.1 BU protocol will suddenly preempt the forwarding packet, and it will start to pick the uh, real-time packet. Let's say the OPC pops up messages, which is done in the host ingress. It started to pick, but the challenge here is how fast you switch, terminate the packet, current forwarding packet, and how fast you pick the OPC pops up messages, and how determinism you are. So for that, we use this hardware-based task manager, which picks the packet from the hardware queues and buffer pools. Um, and then what happens is, like, the task manager will store the uh, program counters and the ALU flags, and then it will execute the real-time task, where it will send the OPC pops up messages, and it will restore the uh, previous tasks that got terminated. So it's completely hardware offloaded. The complete task switch, context switch, will take one cycle, right? So this is one real requirement in a real-time deterministic world, to make faster decision in transmission of packets. And the next one is the uh, three key things. That's the one which I'd like to highlight when it compared to an Ethernet hard IPs, right, which is available in the market. The ICSG gives you an very good flexibility to um, uh, the host and the port buffer pools, right? When you have an buffer pool for the MAC layer to send it, you need a large amount of memory, right? So today, if you see, the amount of memory is calculated based on the QoS, like quality of service. If you have 8 different traffics, you need a bigger chunk. So the challenge what ICSG is solving here is this port and the host buffer pool is completely like configurable. Let's say you are wanted to implement this ICSG in the IO device, right? And you have only one traffic in the sensor, and you don't need 8 different pools, packet pools. You can simply reconfigure it. So in a memory constraint environment, you can make it more ease, and you can make it more easier to use in your resource constrained devices. This is one flexibility what ICSG is going to give when it compared to the Ethernet hard IPs. So it's completely configurable. And second thing is, you see the stream FTP. Today in IEC 60802, there is a requirement that is called stream FTP. That is a little bit different when compared to the hardware FTPs. So these stream FTP, how it actually works is, there is a destination MAC, and there is a VLAN ID in the packet, and it's a combination of DMAC and the VLAN ID, which is used to take a decision whether to forward or send it to the host. So what happens is, when we had this requirement in IEC, like, we didn't have an new ICSS. Rather, it's completely reprogrammable, as I said well before. So it's a small software component in the Mac layer we wrote to make it work. So this is the one successful thing which we done recently for the 60802 support on the stream FTP. So which is very well going to uh, uh, help when compared to the hardware Ethernet hardware IPs. So you can reprogram at any point and add new features, or you can remove features, or whatever it is, right? So then on the left side, you can see the hardware FTP. hardware FTP is again ICSSG has its own hardware-based filter database. Once a packet received or it's supposed to be sent, it has a lookup on the hardware itself and take a decision based on that. Then the last one is security accelerator. This is the one key point which I would like to highlight again. So today in OPC FX world, if you see, there are a need for security accelerators. The reason is because software encryption and decryption takes longer time. So if you're implementing OPC on sensors and you have an encrypted or decrypted IO data, right? It takes more time when you do with the software. So from ICSG, there are like a provision to directly send the messages or the network messages directly to the accelerators, and these accelerators will perform the uh, encryption or the decryption operation and give the data back. So it's not completely relied on the CPU, right? And all security accelerators in our MCUs today have covered the most of the protocols, and it looks like it satisfies all the OPCUAFX security profile requirement. So it's super simple, and you can just simply program it, and there's a uh, um, much more hardware features like context cache. So you can store the keys, IVs, and nonces in the cache itself. And whenever the next packet comes, you don't need to program the keys also. So you can simply encrypt or decrypt it. And OPCUAFX needs such kind of features to make the security faster. And on the other side, you can see the block DMA. That is completely, I would say, if you don't have a security packet and you just wanted to have a faster DMA, then you can use block-based DMA. So if you look into the OPC messages, right, you have an data set, you have a data set messages, multiple data sets, and then finally the network message is constructed. So the DMAs can be programmed in a way that you can um, construct this entire network messages just by passing a packet descriptors to it. So you don't need to do a mem copy or whatever it is. You can packet these kind of network messages at any layer using the block DMA. So, and the last one is that reference implementation. We have an reference implementation for summing up the frames. Like if your frames, like as I said well before, you have DSMs and dataset message and network message. If you wanted to construct all together, you don't need to like uh, put it in the same contiguous memory, right? In DMA, you can program where these chunks are stored and let the DMA to work constructing the frame. So that's the one DMA feature which will also accelerate the packet transfer in the OPCUA world. If that too, we have a big chunk of OPCUA packet, right? So these are the key highlights which we have in our ICSSG module, and which can work along with our MCUs as well. So the next slide is one of the demo which we showcased in AWS Amazon booth, where Amazon team used our TI AM243 product, and they had the OPCUAFX running on top of it, and this was shown on the SPS 2023. So overall, the things we looked into it as of now is key hardware and software requirements required to implement the OPCUAFX products, which ICSG is already satisfying, and it's like pretty straightforward to implement your OPCUAFX product because we have the software, right piece of software already available, where you can pick it and start developing your FX product. And and we also have an engineering expertise to make the FX product on TA platforms, and there is also an vendor neutral stacks available. So this is the like a small abstract on how ICSG is going to take help FX product development. And the one thing is, like, if you have a customer, they are running ICSG in their field, and you have OPC FX component, and you can simply use the ICSG because the ICSG is already equipped with all these things, hardware and soft components, which I explained before. If you have the right software piece, you can simply develop the FX product without need for new product from us. So that's the thing, and I'll leave it for the question. So we have 10 minutes left. If any questions, let me see the comment. We'll see if any questions are there. And so for more information, you can visit our AM64X Industrial Communication SDK and the encoder protocols SDK. And there are tools available, sysconfig, and much more. Right, so there are enough tools also where you can have a look. So I'm looking for questions. Okay, there are no questions so far. So we'll wait for 1 more minute and see if there is any questions around the topic. Okay, so no other questions. So I will leave it to the participants. So if you have any questions, do reach us. And for more information or the updates, you can join the OPCUAFX professional group. There is a LinkedIn forum. You can join there, and the experts there will try to address all your questions and needs. So then we are good. And I think this webinar will be posted on the YouTube as well, and you can have a look at any time. And do reach us if you have any questions. Then thank you all for your time. See you all on the next webinar session, maybe. Yep. Thank you.